Okay, this is the P-series and the integral test. Again, these tests are tests for deciding whether a series converges or diverges. And so they're very much linked. The P-series talks about this particular series, the summation of 1 over n to the P. Okay, so we're going to use this to decide things like, does this converge or diverge? Does this converge or diverge? What about just 1 over n? What about 1 over n squared? Okay, and the P-series is going to say this. Okay, if P is strictly greater than 1, then the series is going to converge. And then, of course, if P is less than or equal to 1, it's going to diverge. And we can explain why, and this is kind of why we're going to link this integral test to this. So this is the P-series, and we just look at the P meaning the power here. Okay, this is a power of 1/2. This is a power of 3. That's just a power of 1. Oh, power of 1, and then this would be, of course, a power of 2. So just by using this test, we would say this diverges, this converges, right? P is greater, the power is greater than 1. Oh, equal to 1 diverges, and then squared is converges. Okay, and this is very similar to improper integral stuff that we did. And again, I want to explain kind of why these do what they do, and that's really what the integral test kind of can justify the P-series stuff. Okay, and I guess another thing I want to throw out is, what if there's a number here? What if this isn't a 1? What if this is 4? What if this is 5? Well, that's completely irrelevant, right? Because if this is an infinite sum, then clearly 5 times that. If I put a 5 up top, 5 times that is still infinite. If this is a converging sum, then 5 times some finite number is also just a finite number. So putting a 5 or a 4 or a 10 here or a 3 here, those are not going to affect this. Really, it's this polynomial power here is the controlling factor. So, you know, if it's this 4 over the square root of n, it still does the same thing. If this is 5 over n cubed, it still converges. If this is, you know, 1 over 3n, it still converges, or excuse me, it still diverges. This is just 1/3. That 1/3 can be factored out. That 5 can be factored out. That 4 can be factored out. These numbers are not going to change really anything, because a finite number times an infinite sum is still an infinite sum, and so on. Okay, so now we do the integral test, and here's what the integral test says. It says that if you can show that, like, this integral, the integral of some sort of function, x, like 1 over x squared, we'll just do an example. If that converges, then it does the same thing as the corresponding series. Okay? The integral test doesn't say which one does which. It just says, though, that this is the corresponding integral to this series, that this series and the integral either both converge or both diverge. Now, we already showed this when we did our improper integrals, and if you haven't done that, well, then you should go back and look at those videos or those lessons to look at improper integrals. We can show that this guy converges, and again, we can just do the integral. The integral from 1 to infinity of 1 over x squared is negative 1 over x from 1 to infinity. Plugging in infinity, I get negative 1 over infinity minus 1. So this whole thing is just 1. What I've shown here is that this particular integral, I've shown that this integral from 1 to infinity of 1 over x squared dx converges, meaning it has a finite area of 1. Thus, based on the integral test, the series from 1 to infinity of 1 over n squared also converges. Now, I'm not claiming it converges to the same number. That's not what I'm saying. But they do the same behavior. Maybe I should say not same, but same behavior. Because they are not the same thing. This is a very discrete thing, letting n go 1, 2, 3, 4. And this is a continuous integral of doing all the x values from 0 to infinity. This is the area under the curve, and this is a finite sum of things. But they have the same behavior. So once I know that the integral converges, then the series also converges. And so I can use this to show that if p, as we did on the p series with integrals, that if this power is greater than 1, I get a converging integral, thus a convergent series. And again, I can do the example of let's say this one. I can show that this integral from 1 to infinity of 1 over x dx equals the natural log of x from 1 to infinity, which is the natural log of infinity minus the natural log of 1. The natural log of 1 is 0, but the natural log of infinity is infinity. And so what I have here is I have that this integral diverges, so dot 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 by the integral test, this corresponding series also must diverge. Okay, this diverges because this diverges. They have the same behavior. So if you're interested in whether a series converges or diverges, you can use the integral test. Now, we have this special p series. Anything that has this exact form, then we don't have to do the integral test. We can, all right, boom, it's just kind of done. It gives us kind of benchmark for saying, okay, this is the controlling factor. Now, if something is not exactly like this, then we have to do some integral test to maybe decide. But these two are pretty much used for the same thing. Okay? So what I mean by that is we're going to use the fact that we understand p series, and we can do a variety of other ones that are pretty much that same thing. Okay? So what if I had the series 3 over n plus 1? From n equals to 1 to infinity. Okay, so technically you can't use the p series because this isn't just something over n to the p. That plus 1 messes everything up. However, we know that this is pretty much, that 1 doesn't do much. This is pretty much 3 over n. And 3 over n diverges based on the p series test. Now, some people aren't going to like that because it's not technically p series. So what you're going to have to do for them is you're going to have to do the integral from 1 to infinity of 3 over x plus 1 dx, which is 3 natural log of x plus 1 from 1 to infinity. And you still get 3 times the natural log of infinity minus 3 times the natural log of 2. That's some finite number, and this is infinity. And still get infinity. And so by the integral test, this integral diverges, thus the corresponding series also diverges. And we knew it diverges because when I'm letting n be infinity, this plus 1 doesn't do anything. This and this are pretty much the same once n is big enough. And since we know this diverges from the p series, of course this diverged. And again, it's one of those things that's going to be dependent on your professor, depending on your teacher, of what proof you really need to show me. Both the integral test and the p-series test pretty much show something like this, converges or diverges. And then later on, I'll even show you another test that kind of does the same thing, called the comparison test, where we can use it in a variety of ways. We could do something. What if we did something like 2 to the n over n squared plus 5, something like that. And again, for me, I'm going to say, you know what? That's an 2n over an n squared. That's pretty much 2 over n. And if that's 2 over n, then I know this thing diverges. And again, you can't really claim that the p-series, because this certainly doesn't look just like a p-series, but you could use the integral test, so you could integrate this thing. The integral from 1 to infinity of 2x over x squared plus 5 dx. And if you do a u substitution, if this is your u, x squared plus 5, then that's du, 2x dx. And so this thing really just becomes the integral of du over u, which is of course the natural log of u, x squared plus 5, from 1 to infinity. The natural log of the natural log of infinity squared is still just infinity minus the natural log of 6, and you still get infinity, which says that this integral diverges. So of course then the series diverges. And again, it's just another way to show that this is in fact pretty much 2 over n. Okay, let's do one more and let's make it converge. Let's do a fun one, like how about from 0? Oh, that's not what I want. I'll write that first because I'm going to answer the question. This guy. What if I had this? 1 over n squared plus 1 from n equals to 0 to infinity. Now again, it's not technically p-series, right? It's not 1 over n squared. It's 1 over n squared plus 1. But guys, really, 1 over n squared plus 1 is pretty much 1 over n squared. And we know that 1 over n squared converges based on the p-series test. And then we can prove it using the integral test. So let's integrate the corresponding function, 1 plus x squared dx. And we know that integrating 1 over 1 plus, well, we know that's actually just inverse tangent of x from 0 to infinity. So then that's inverse tangent of infinity minus inverse tangent of 0. Inverse tangent of infinity is actually just pi over 2 minus 0, and we get pi over 2. And again, let's draw the graph of tangent to remind ourselves why inverse tangent is what it is. So there's your graph of tangent. Remember, tangent of pi over 2 is infinitely big. So then inverse tangent of infinity is back to pi over 2, right? Tangent of this angle as an infinite ratio. Inverse tangent of that ratio spits back that angle. And again, so inverse tangent of infinity is pi over 2. This converges, right? It's a finite area. But if the integral is finite, meaning the integral converges, then the corresponding series converges, but of course it does because we know that that plus 1 doesn't do anything. Again, I just want to remind you that the p-series and the integral test are very similar in that they both tell us situations where it's something like 1 over np or an n over another n. It's like polynomial stuff. And again, we really want to say that this is kind of that barrier. If the overall power is greater than 1, then it's going to converge. If it's going to be less than 1, then it's going to diverge. And those smaller things don't matter as much. And again, I tried to show that if you have an n over an n squared, it's pretty much something over n, which is going to be diverge. This is a 1 over n squared plus stuff. It's going to converge. And again, you can go through these, and you should be able to now use the p-series and even the integral test to do things to justify pretty quickly whether or not you think something converges. What if this was 5 square root of n plus 1 over n cubed? What do you think? Well, this is like a half, and this is 3, and so this eventually is going to be something like 5 over n to the 5 halves, which converges, because this is greater than 1, right? This is bigger than 1 over n. You know, you could do n plus 1 squared over 4n cubed. Well, this is pretty much an n squared up top over a 4n cubed, which is pretty much 1 over 4n, but that diverges because this is a p-value of 1. And again, this doesn't technically fit p-series, and it would be very difficult to actually do the integral, but eventually we'll do some comparison tests where you can boil this down to its basics, and then based on the basics, you know what happens to this. If p is greater than 1, it converges. If it's 1 or less than 1, it diverges, right? This is a p-value, a power of 1. This is a power greater than 1. This converges, this diverges, and then we can go on using a p-series and integral test kind of combo to decide whether things converge or diverge. Okay?